This video covers section 1 of chapter 11 on categorical and quantitative variable inference using a paired design. We'll look at different ways we can frame inference for a relationship. We'll talk about the categorical explanatory and quantitative response variable relationship and remind ourselves of the three possible designs. We'll focus on inference for a paired design, and we'll talk about paired versus ordinary and using the t-distribution versus the z-distribution. Additionally, we'll cover chapter 2 on a two-sample design. We'll talk about the sampling distribution of the difference between means. We'll use the two-sample t-statistic to perform hypothesis tests. We'll perform the test using software and by hand. We'll construct two-sample confidence intervals, and we'll look at the procedure when our samples are pooled. In the 4 stages of statistics, we are in statistical inference. We're looking at a relationship between categorical and quantitative variables, and we're going to focus on paired and two-sample designs. Now, there are 2 approaches for inference for relationships. One is the null and the alternate hypotheses are about variables, whether they are related or not. This is something that applies to all 3 of the relationship styles between variables. We could also frame our inference question in terms of null and alternate hypotheses about parameters, whether they are equal. In this case, we might ask whether the population means for the 2 different categories are equal. Or, if we're talking about paired, whether the difference in the means is 0. When we're talking about categorical to categorical, we'll ask whether the population proportions are equal. And for quantitative to quantitative, we'll use regression and ask whether the population slope is 0. In all of these, we'll often do the hypothesis test before we compute a confidence interval. The test tells us if the variables are related. If they are, the confidence interval tells us how the relationship works and how different the parameters in question are. Here's an example. For all students at a university, are the math SATs related to what year they're in? How would we frame this question in terms of parameters? Well, we're looking at 4 different populations, maybe even 5 if we count other. And the question is, are the mean SAT scores different for each of the 5 groups? This is a question we'll answer using analysis of variance, which will be in the next video. In this one, we're going to focus on paired and two-sample designs. So remember, there are several different possible designs for a relationship between an explanatory categorical variable and a quantitative response variable. There's the paired design, the two-sample design, and the several sample design. Before we decide which analysis technique to use, we have to first decide which design we're studying. For paired, we use exactly the same techniques as we did for one sample t distribution. For the two-sample design, we'll use a two-sample t, which works in much the same way as the one-sample t. For several sample, we'll need a new distribution called the F distribution. Here's a question. Are age of parent and sex of parent related for population of students at a university? So here's our data set. It comes from the student survey data. How can we answer this question? We'll look at sample differences, dad's age minus mom's age, to test if the mean difference is 0. Because this is a paired design, we're going to be really interested in that difference of ages. Now, there are 2 ways to look at this. In the first way, a two-sample design, we lump all the dads together and all the moms together. But the dads and the moms are related. Each student at the university has one of each. So what we really want to do is pair up the corresponding dads and moms and find the difference in their ages. So for this example, our question is, which of these two outputs from statistical software has enough information to do inference? This is a paired design, so we need to look at age differences. We need the mean and the standard deviation. Because these two variables are related, because it's a paired design, the individual standard deviations of the dads and the moms doesn't contain enough information for us, because those variables are related, they're dependent. So to check for a relationship between the variables, let's look at this data set of differences in ages. Which parent tended to be older in the sample? Well, we did dad's age minus mom's age, and I see that mean is positive, so dads overall are older than moms. How will we display this data? A histogram is the best way to do it, and we'll construct a histogram looking at the differences. Here's what it looks like. We've seen this histogram before. Our null hypothesis in this case is that the two variables are not related, dad and mom. So the null hypothesis would state that the difference in the ages should be 0 if there's no relationship. The confidence interval that we're going to create will be centered at x bar, as usual. So here's the histogram again. What do we see? Well, the difference in ages is centered at around 2.5. You see it labeled on the graph with x bar. The spread looks like it's about 2 or 3. And the shape is skewed to the right. We see a nice long right-handed tail. Now, for notation, when we're looking at a paired study, we indicate differences by, in the sample mean of the differences with an x bar and a subscript d. The population mean would be mu with a subscript d. Again, that d implies differences. The sample standard deviation will be s sub d, and the population standard deviation will be sigma sub d. So what test statistic should we look at? Well, we'll start by just constructing t as we always have. Sample mean minus population mean hypothesized over the sample standard deviation divided by the square root of the sample size. Since we're looking at differences, we'll use x bar sub d and s sub d. For paired studies, the null hypothesis will always claim that the mean of the differences is 0. So that mu naught will always be 0 for a paired study. So this simplifies down to this expression. So here's the output for the test. We see the dad's age, the mom's age, and the differences, the mean, standard deviations, and standard errors for mean. We see the 95% confidence interval. And the t-test has a t-value of 13.11 and a p-value essentially 0. So what did we learn? Here you see the null hypothesis, the test of the mean difference equals 0, versus that it's not equal to 0. Is this unbiased? Yeah. Is n equal to 431 large enough? Because remember, our data, the sample data, looked pretty skewed. But yeah, I think so. 431 is a really big sample. Is the population big enough so that the sample means ought to be distributed normally? Sure. The population is greater than 4,310. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . The sample mean is 2.448, so our t-value we would compute as 13.11. Is that large? Oh yeah, that's really big. Our p-value is essentially 0 to 3 decimal places. Is that small? That's about as small as you can get. So can we conclude that the population mean difference is 0? That's the null hypothesis. Absolutely not. We're going to reject the null hypothesis. So the answer to our question, are sex and age related? Definitely. Just like in the regular t-test, the alternate hypothesis could be one-sided or two-sided. We just looked at a two-sided paired test. We were testing whether the mean difference was 0 versus the mean difference is not 0. What would change here if we'd suspected ahead of time that fathers tend to be older than mothers? Well, that would change our alternate hypothesis. Instead of is not equal to, we would use a greater than. Of course, the one-tailed or one-sided alternate hypothesis results in a p-value that's half as big as the two-sided. Half of that value that's approximately 0 is still approximately 0. Would we still conclude that fathers in general are older? Absolutely. Sticking with this example, what do we know about the p-value? The paired t is the same as the ordinary t distribution. We just have one statistic. When n is large, the t distribution and the z distribution are about the same. So that 13.11 as the t statistic would be interpreted in terms of z as 13.11 standard deviations above the mean. That's definitely an unusual z value. So if we had done a z-test, we would have gotten a p-value approximately 0 as well. Is that strong evidence? You bet. So remember, if the t-value is unusually large, and think of it in terms of z, we don't need software to do this. 13.11 is huge. Now let's look at confidence intervals. When we don't know the population standard deviation, the 95% confidence interval is computed as the sample mean plus or minus a multiplier times the standard error. That's the standard deviation for the sample over the square root of the sample size. That multiplier comes from the t distribution with n-1 degrees of freedom. The multiplier is always going to be at least 2, and it's going to be closer to 3 if n is very small. So the confidence interval for the mean of the differences is computed in much the same way. It's the sample mean of the differences plus or minus a multiplier times the standard deviation of the differences in the sample over the square root of n. That looks very similar to the last formula. Again, the multiplier is coming from the t distribution with n-1 degrees of freedom. The multiplier is smaller for lower confidences and higher for larger confidences. The multiplier is also smaller for larger degrees of freedom and bigger for lower degrees of freedom. If n is small, to compute this confidence interval, the differences need to be distributed approximately normally. This is exactly what we saw for the regular old one-sample t-test and t-interval. So we'll use very similar guidelines for when the sample mean differences are approximately normal. We'll assume that the shape of the random variable for sample mean differences with n pairs is approximately normal if the graph of the sample differences appears normal, so we'll need a histogram or a stem plot or something like that, or the graph looks symmetric and n is at least 15, or the graph is relatively skewed and n is at least 30, or the differences are very skewed and n is much larger than 30. That's the situation that we saw in the parents' ages. That was a pretty skewed distribution, but n was in the 400s. That's very much larger than 30. So, looking at the same set of data, Let's construct a 95% confidence interval for that population mean age difference. Because n is large, we can use the same t multiplier as we got from the z distribution. This is a 95% confidence interval, so we'll use 2. So the confidence interval is 2.45, that's the mean in the sample, plus or minus 2 standard errors, which gives us a confidence interval of 2.08 to 2.82. So we're 95% confident that fathers in the population are older by somewhere between 2.08 and 2.82 years. Looking at the histogram, that seems reasonable. Here's another example. Here are the mileages in miles per gallon for 5 cars. One for those are usually reported with 2 numbers, a city number and a highway number. We suspect that cars in general get higher gas mileage on the highway. Is it appropriate to use a paired t procedure? The histogram is more or less normal. There's a peak in the middle and the tails, maybe the right tail is a little bit heavier, but overall it doesn't look too bad. Here's what we get when we run this through software. What do we learn from the output? Well, we get a p-value of 0.2%. That's pretty strong evidence. So location, we could conclude, does play a role in miles per gallon. Confidence interval tells us that we're 95% confident the highway average is somewhere between 3, that's where we see that negative 2.98, and 7.8 miles per gallon better in the population. So again, that 3 is coming from that negative 2.98, and the 7.8 is coming from the negative 7.82. I know that we need to switch these because our output tells us that we're doing city minus highway. That's what tells us that highway average is higher. If we were doing this by hand, what do we need for the 95% confidence interval? Well, we know the mean, we know the standard deviation in the sample, and we know the sample size, so all we need is the multiplier. The sample size was 5, so there are 4 degrees of freedom. We'll use our chart to get the appropriate multiplier, and it's 2.78. So our interval is negative 5.4 plus or minus 2.78 times the standard error, which gives us an interval from negative 7.82 to negative 2.98. Here, because n was small, that tells us the multiplier for 95% confidence is going to be closer to 3 than it is to 2. How do these two things relate? Well, notice that 0 is not in the confidence interval. The small p-value led us to reject the null hypothesis, which was that the difference in the population had mean of 0. Our confidence interval reflects that. 0 is not in the confidence interval. What happens when we switch the columns, if we switch the role of city and highway? Well, we ought to see much the same thing, except all the signs are going to change. The inequality is now greater than instead of less than. The mean of the differences would be positive, and the t-value would be positive. The p-value would still be the same, though. Therefore, it doesn't really matter which direction you do the subtraction, as long as you interpret it consistently. The data on the left show math and verbal SAT scores for a sample of 12 students. I wonder if overall the math scores and the verbal scores are about the same, or if they're different for each student. Since this is a paired design, we're interested in looking at the differences for each person. So go ahead and enter the data you see on the left for math in L1 and for verbal in L2. I've already done this, so pause the video and go ahead and punch those in your calculator. When you're done, we want to take a look at the differences. So to compute those, I'm going to go over to L3, and to compute the differences easily, I'm going to push the up key to select L3, and now here it says L3 equals. I want L3 to be equal to L1 minus L2. And now my calculator computes all those differences for me. Now we're ready to do a t-test on the differences. I will quit out of this. I'll go back into my stat menu, and I'll go over to tests, and I'm going to perform a t-test. Here I'm going to input data. Because this is a paired design, the null mean is always 0. The list I want to use is L3. Remember, that's where our differences are. The frequency will be 1, and since I don't have any reason to suspect that one of these scores would be higher than the other one, I'm going to test this against a two-sided alternative. And we'll calculate. Look how small our t-value is. It's very close to 0. Our p-value, sure enough, reflects that. We get a p-value of 0.93. That's enormous. In fact, the mean of all of those differences was only 1.6666, etc. That's essentially no difference at all. That's kind of what we expected. So remember, when we have a categorical explanatory variable and a quantitative response variable, we may have a paired design, which reduces to a one sample t. We just saw that. For this design, we look at the mean of the differences. There's a two sample design. For this, we'll use a two sample t, which is going to be similar to what we've done for the one sample t. We're about to talk about that. For this, we focus on the difference between the means, not the mean of the differences. We also have the several sample design, which we'll look at in the next video. So let's turn our attention to the two sample t. For a two sample design, we display with side-by-side box plots, one for each categorical group. We want to make sure that our box plots have the same scale. To summarize, we may look at the 5-number summaries, which we get from the box plots. We also will compare the means and the standard deviations. It's the latter one that we're going to focus on in our inference techniques. Let's look at notation. For the sample sizes, we'll use subscripts 1 and 2 on the ends. So N1 is the size of the first sample, and N2 is the size of the second sample. We'll use similar notation for the other things we're interested in. For the sample means, we'll put subscripts 1 and 2 on the x bars. For standard deviations, we'll put the 1 and the 2 as subscripts on the s's. In the population, we'll do the same thing for the means and the standard deviations. So how do we do inference for two samples? The inference we want to do will be about the difference of the means in the populations. The test is always going to be, is that difference 0? Just like in the paired design, our null hypothesis is that something is equal to 0. If the difference in the means is 0, that suggests that there is no relationship between the variables. For confidence intervals, if the difference is not 0, how different are they? Remember, in the past, we estimate the population mean with the sample mean. And then we looked at how the random variable of all sample means is centered, spread, and how it's shaped relative to that population mean. So now what we're going to do in light of what we've done in the past is we're going to estimate the difference of the population means with the difference of the sample means. This is a new random variable. The x1 bar is the random variable of all possible sample means from the first population, and x2 bar is the random variable that consists of all the possible sample means taken from the second population. What should that look like? Well, as a random variable, it should be centered at the mean from the population. If the samples are unbiased, that means the center should be at mu1 minus mu2. For the spread, well, this is a little bit more complicated. Remember, we can't add and therefore we can't subtract standard deviations. We have to first convert to variances, then add, and then take the square root. The shape will be approximately normal if the sample means are normal. So for two-sample inference, our claims, that is our null and alternate hypothesis, will always be that the difference between the population means is 0, that's the null hypothesis, or not 0, that's the alternate hypothesis. This is equivalent to claiming the population means are equal or not equal. Do you see that these equations are the same? If you take this first one and add mu2 to both sides, you get the second one, the one below. And for this inequality, if you add mu2 to both sides, you get this one below. So to compute t, we will do exactly the same process that we always have. We'll look at what we're interested in the sample. We'll subtract what we think is true, assuming the null hypothesis about the population, and we'll divide by the standard deviation. Here's what it looks like. In the numerator, we'll have the difference of sample means minus the difference of population means over what we've computed to be the standard error. Because we're assuming the null hypothesis is true, that means that the difference mu1 minus mu2 is 0, which simplifies our computation a little bit. The shape of this distribution is bell-shaped and symmetric, centered at 0. But it's not quite the same as the one sample t. Our statistic that we've just computed, t, will follow a two sample t distribution only if the sample means are normally distributed. The two sample t distribution is like the one sample t, but degrees of freedom is hard to compute. It's somewhere between the smaller sample size -1 and the sum of the sample sizes -2. You're not ever going to have to compute the degrees of freedom by hand. Your calculator will do it for you. If the sample sizes are large enough, the two sample t looks a whole lot like z. Here's what we get. This looks familiar, right? The z distribution is in black, the t distribution is in red. So remember, when we're looking at the one sample t, what could make t big? When we simplify that fraction, we see that t is big if the difference in the sample mean and the population mean that's hypothesized are far apart, if the sample size is big, or if the standard deviation is small, the standard deviation in the sample. So what about the two sample t? Here's our formula. We can't simplify it quite like we did before, but a similar thing is going to hold. If that difference is big, t is going to be big. If the sample sizes n1 or n2 are large, notice how they're in the denominators of a denominator. So making them big will make the fractions in the denominator small, which makes the whole big fraction big. And similarly for the standard deviations S1 and S2. If they're small, it's going to make the fraction under those individual fractions under the radical small, which overall will make the big fraction large. So what's the effect on the p-value? It's just what we've seen before. If t is big, we get a small p-value, and vice versa. What about standard deviation? Here we see box plots. That's the way that we display this relationship. In both, the sample means are the same. X1 has mean 3, X2 has mean 4. The box plot on the left has a big standard deviation for each. The one on the right has a smaller standard deviation. Which of these makes the difference between the means seem more significant? When the one on the left, each mean falls within the box plot middle 50% of the other one, but on the right it doesn't. That less spread means the boxes don't overlap as much, which means we're more confident that the difference in the means that we observe is a real difference. So what does that mean for our p-values? For which of these are we more likely to reject the null hypothesis? Definitely the one on the right. The smaller standard deviations mean we have a larger t, which results in a smaller p, which makes resulting the null hypothesis more likely. What about sample sizes? Here we have the box plot that we saw on the left before. Which of these would give you more evidence to reject the null hypothesis if the sample sizes were each 5 or each 12? Remember, bigger sample size means stronger data. Stronger evidence will make us more likely to reject the null hypothesis. So here's the software output for a 2-sample t-test. So can we conclude that student sex tells us something about age? If so, what does it tell us? Well, here we get a p-value of 0.32. That's not very small. So do we think age and sex are related? I would say no. Are the sample means close? Yeah, they're pretty close, especially if you compare them to the standard deviations. So can we conclude that the difference between the population means might be 0? Could be. How do we do this by hand? Here are the summary statistics. We have sample sizes for both, we have means for both samples, and we have standard deviations for both samples. If we want to know if age and sex are related, we first formulate our hypotheses. Our null hypothesis for 2 samples is always that the population means have a difference of 0, and the alternate is that the difference of the means is not 0. We'll standardize, that is, compute t. And remember, t is the difference of the sample means in the numerator. In the denominator, we square those standard deviations to get variance. We divide by the sample sizes, we add them together, and then take the square roots. Whew. That gives us a t-value close to -1. Because these sample sizes are big, we can use the z distribution. Since t is close to -1, that means that the area in the tails that are farther away from the mean than t is would be the area of the tails for z equals +1 or -1. I know that the area between +1 and -1 on the standard deviation, the standard normal distribution is about 68%. So that means the area in the tails is around 32%. Is that a small p-value? Nope. So do we have evidence that sex and age are related? No. What we saw from the software is consistent with what we found by hand. We got a p-value around 32%, and that's pretty close to what the software gave us. We were able to do this by hand because the samples were large, so we could use the z distribution. We saw that our t-value was very close to -1, so in absolute value, t was around 1. That gives us the p-value of around 32%. How do we compute confidence intervals? It's much the same thing that we've seen before. We take our difference of sample means, we add and subtract some multiplier times the standard error. The multiplier comes from the two-sample t-distribution. And as before, the multiplier is smaller for lower confidence, and it's smaller for larger degrees of freedom. If the samples are large, we can use 2 for the multiplier. So for our age and sex that we've been looking at, what's the confidence interval? Because the samples are big, we can use 2 as our multiplier. That gives us a confidence interval about -3/4 to +1/4. So we're 95% confident that females are between 3/4 of a year younger and 1/4 of a year older than males on average. Notice how we're using younger and older to interpret that difference. So 0 is in our confidence interval, and that's consistent with our hypothesis test. If we look at a 95% confidence interval for difference between population mean heights in inches for females minus males, we get -6.4 to -5.3. What does that tell us? Well, it tells us that we're 95% sure that on average females are shorter by between 5.3 and 6.4 inches. This would lead us to reject the null hypothesis that the means of the males and females' heights are equal. If we change the order of subtraction, if instead of doing females minus males, we did males minus females, what would that change? Well, remember, that only changes the signs. Our confidence interval would be the corresponding confidence interval we'd get by changing the signs. Notice 5.3 is smaller now, so it goes on the left. Now, if we can assume that the population standard deviations are the same, the standardized difference follows the actual t-distribution. The number of degrees of freedom is the sum of the sample sizes minus 2, which really, that's n1 minus 1 plus n2 minus 1. Everything that we've seen before still holds. Higher degrees of freedom means a narrower confidence interval. There is a rule of thumb. We'll use the pool t if the larger sample standard deviation is not more than twice the smaller. So look at these. Here are some possible sample standard deviations. To check the rule, find the smaller standard deviation and double it, and see if that's bigger than the larger one. In the first case, it's not. So we can use the pooled technique. In the second case, it is. So the pooled technique is not okay. The data on the left show the number of minutes exercised for a sample of females and a sample of males taken from our student survey data. I suspect that the males work out more than the females overall. So let's test that hypothesis. First, let's enter the data into L1 and L2. I've already done so, but you should take a moment to do the same. Once you got them punched in, we will quit out of this, go back to stat, to tests, and we will do a 2-sample t-test. I've already got the data put in, so I'll leave that in, leave that where it is. If I knew the means and the sample standard deviations ahead of time, I could just select stats and type those in directly. But I've got my first set of data, the females in L1, the males in L2. Each frequency will be 1. Now I suspect the males work out more than the females. So I'm going to select my alternate hypothesis is that mu1 is less than mu2. That is, the average for females is less than the average for males. Now we come to pooled. I'm not sure whether it's appropriate to do a pooled test or not. So I'm going to select no. And now we calculate. We got a t-statistic of -1.05 and a p-value of 0.15. So we wouldn't reject the null hypothesis. But let's go and make sure that we made the right decision about pooled versus not. Notice that the larger standard deviation is for the males. If I cut that in half, I get something a little more than 25, which is less than the standard deviation for the females. That means I could have used the pooled technique. So let's go back and make sure that doesn't change anything. So I'll go back into stat and tests. I'll do a 2-sample t-test. Everything should still be in here. I'm just going to go down and change that pooled to yes. And when we calculate, we'll see that didn't really change our p-value all that much. What really changed is the degrees of freedom, and the p-value changed, but just a little bit, not enough to affect the outcome. So we do not have sufficient evidence to reject the null hypothesis. The average amount of time for females and males working out should be about the same. To sum up, in this lecture, we talked about inference for relationships between two variables. We looked at the variables in particular, as well as the parameters related to the variables. We looked at the relationship between a categorical and quantitative variables. We reviewed the 3 different possible designs: paired, 2-sample, and several sample. For paired design, we looked at the output, the display, the notation, the test statistic, t, and the form of the alternative. Remembering that for paired designs, we're interested in differences. So we perform hypothesis tests using a single t-test. We looked at the paired t versus the ordinary t versus the z, how they were distributed. And we computed a paired confidence interval and a paired hypothesis test. We also talked about inference for a 2-sample design. We looked at that notation, the test we perform, how to create confidence intervals. We talked about the sampling distribution of the difference between means. We looked at the 2-sample t-statistic and how the role of the difference between sample means, standard deviation sizes, and sample sizes will affect the outcome of our hypothesis tests. We performed the tests mostly with software, but also by hand. We created a confidence interval. We talked about pooled versus unpooled 2-sample t procedures.